Is it working? Okay. I will begin with a word of prayer. So, Dearly Father, we thank you for this day. Thank you for the weekend, and again for the nice weather. I just pray that you'd be glorified in what we do, and that we just use this time wisely to prepare for test 2, Lord. In your name I pray, Lord Jesus. Amen. All right, let me fire up this projector here. So you guys have any questions while I'm firing this thing up?
Did you say you only graded the 3 problems?
Yes. That is correct. That's what he said. And then he said he graded 3 and he doubled the deductions, assuming that you guys did most of them. Let's see here. If I can find my solution, that would be great. Where'd it go to? Well, I posted the solution in, did I post the solution in Canvas?
Yeah.
Okay, good. Because I must not have ever saved it on my computer. That's not good. Come on, computer. Well. All right. We are in differential equations, I think. There we go. Come on. We'll get there eventually. All right. So do you guys have any questions about any particular one here? Let's see here. Let me talk about a few of these here. So this one, you're supposed to find the annihilator, I think, and the minimal annihilator for each of the following functions. So let's see here. For e to the x, I do a d minus 1. For the sine 4x, I do d squared plus 16. You put these together, that's the lowest order differential operator will kill that thing. To kill x squared, I need an x cubed. To kill cosh, I need a d minus 1 and a d plus 1, right? Because it's got both exponentials in there. Or you can just remember if you got cosh, you use d squared minus 1. So that's kind of a little bit of a shortcut, right? If we've got cosh of beta x, we could use d squared minus beta squared as an annihilator. The te to the minus 3t means that we had a lambda equals to minus 3 repeated, which was why I put a d plus 3 squared here. And then the d is to kill the 2. Now part d here required some trigonometry, right? Like there's no easy way around that. You just kind of got to face the music And here's how I do that. I use imaginary exponentials to convert my given product of cosine and sine to a sum of sines. So as you can see, it's sine of 4x, sine of 2x. And as such, I can use d squared plus 16 to kill that guy, and d squared plus 4 to annihilate that fellow right there. So, yeah. Now, you don't have to use imaginary exponentials to do this kind of thing if you don't want to. You do guys get a 3-inch by 5-inch card. You can put whatever you want in there. And perhaps you might want to put like the product of cosine sine, or the cosine cosine, or the sine sine identities, you know, just in case you don't know those. I mean, I don't know those off the top of my head either. I derive them with imaginary exponentials whenever the problem comes to me, because it's just easier than looking something up. Let's see here. So another one I'll talk about. So then the next problem was to use, basically this is built off the previous one. Right now I say set up, but do not explicitly determine the coefficients of the form of yp by the method of annihilator. So basically I just use what I did in the last problem, annihilate both sides. It gives me, you know, this. I combine any like factors. In this case, I think there's a d minus 1 that's common to both L and A, the annihilator and the differential operator that defines the differential equation, right? Maybe we could call this the homogeneous operator. So I don't know what you want to call it, but I don't really have a name for it. I just call it L. Anyway, the point is that this and that are part of the homogeneous solution, so they can't be part of the particular solution. And as such, everything else that's left over must be the form of the particular solution, right? So there it is. That's the setup. And that's as far as it goes, right? If you're setting up the particular solution minimally, that's where I'd stop, right? If I'm going to go past that, I have to do algebra. I have to plug it in and stuff, right? Setting up the particular solution for a given problem shouldn't take you more than about 3 or 4 minutes, right? Finding the particular solution carefully, that could be more like 5-10 minutes. Well, I don't know. It depends on the problem, but here's another one. Again, every time the same strategy. Find the annihilator for the forcing function, annihilate both sides. That gives me a higher order problem. I write down the general solution. I get rid of the part which I don't care about, which is the homogeneous piece, which is this one and that one for this problem, which means everything else there is the form of the particular solution. And that's the lowest order you can get away with without getting into details, right? So here's another one. So I annihilate both sides. I have d plus 3 squared. Because I have a d plus 3 for the annihilator. I have d plus 3 squared for the annihilator. I have a d plus 3 inside the L. So I end up with a d plus 3 cubed when I multiply it all out. And then I get a d times d, which is d squared. So that would be my general homogeneous solution to the corresponding homogeneous problem. Of that, we can identify that this term, and this term are the particular solution. And I just, you know, as I've told you guys before, I think it's really neat. The annihilator method like automatically knows to multiply, you know, the naive solution by t in this case, but multiply the, well, also to multiply the naive solution by t in this case, right? I mean, it's like, it's very cool. But I think what's more impressive is the annihilator method, you know, just multiplies the part that needs to be multiplied by t and no more, you know. This one here, well, anyway, we've gone through these, so I'm going to skip ahead a bit here. So this I left in as a cautionary tale, right? So I tried to solve this. What am I up against here? Lambda squared minus 4 lambda. So that gave me a homogeneous solution of, you know, c1 plus c2 e to the 4t. And I just naively put down yp as a plus bt plus c e to the t and see what happened, right? Differentiate again, plug it in, and what I get I find myself faced with 3 minus 3c e to the t minus 4b equals 6t plus, but I can't achieve that, right? Because if I equate coefficients of t on both sides, I've got 0 equals 6. That's not good, right? And so like that's impossible. So what if that happens to you? What does this mean? This means that you set up the particular solution wrongly. All right? And so you need to go back and adjust it. And this one, we needed to multiply the naive solution, the part of it that corresponds to the polynomial, by t because there was a constant term in the homogeneous solution. So yp should be this, which when we differentiate, we get that. And when we plug that in, then the algebra works out, as it is shown down here. You know? So if I differentiate, plug it in, and as usual, equate coefficients, constant terms have to be 0. There's no constant over there. I've got a minus 8a here, which has to be equal to 6 over there. And I've got minus 3c on the exponential. I've got a 1 over here, which gives me that. And do the algebra, and out pops this. Of course, without initial conditions, we do expect for a second order problem that there are two constants in the solution, right? On the other hand, if I'm given like an initial position and an initial velocity, then you expect that there are no constants in the solution, right? You'd expect that you can work it out, and you know, you wouldn't have any floating constants. Here we go. For my attendance sheet. This one's a little old. We'll bring it. We'll put it back to service. It'll still work. It's still got some life in it. All right, let's move along here. So this one is exactly such a problem that I have initial conditions, right? I have y of 0 is 0, y prime of 0 is 1. In this problem, the characteristic part is d plus 1 squared, whereas, you know, the annihilator for this over here is d squared plus 1 times d. So this is a standard mistake you guys make. Like it's just very popular, very, very popular mistake is to confuse this animal right here with this animal right here. Don't let this happen to you. These are radically different, right? D plus 1 squared has real, you know, the corresponding characteristic equation, lambda minus 1 squared equal to 0. That gives me lambda equals to minus 1 twice. Whereas this, if I look at the corresponding algebra equation, lambda squared plus 1 equal to 0, I get lambdas plus or minus I. These are really, really different. And the solutions are radically different as well. But that's good news for us here, because it means we don't actually need to use the annihilator method, right? We've done enough here to see that the naive solution will work, right? So I just take derivatives. Some of you guys came up to me after class, you're like, how do you formulate the naive solution? Well, basically you just look at the forcing function, take some derivatives, see what happens. So in this case, cosine differentiates to sine, and the 3 differentiates to nothing. So basically your naive solution is linear combinations of sine and cosine and a constant. Differentiate that, differentiate it again, plug it in, and do the algebra. What do we get? We get this mess down here. So we get c equals 3, a equals 0, b equals a half. That brings us to the general solution. This general solution is what you should always apply initial conditions to. Another popular mistake to make in here is to try to apply initial conditions to the homogeneous solution. It's a very unfortunate thing that we call it a solution, because the homogeneous solution is not actually a solution to a non-homogeneous problem, right? Because when you plug it in, you don't get 0. I mean, you get 0, you don't get the forcing function, right? The actual solution is here, and this is called the general solution because your ability to manipulate the values for C1 and C2 reflects the possibility of fitting any possible initial condition to this problem. And so we have y of 0 is 0, which gives me C1 plus 3, so C1 is minus 3, and then I have to differentiate, right? Which could be annoying, like you're going to have to differentiate, you do some product rules and stuff. But if you look at where you're going, a lot of times most of the stuff you're differentiating is 0 anyway, once you plug in the constant. But anyway, here after a bit of algebra and calculus, we end up with minus C1 plus C2 plus a half equals 1. So I get C2 is minus 5 halves. And then finally, put it all together, here's my solution to the initial value problem here. So there's usually a problem like this on the test. Something like this is pretty appropriate for the test. This one here, I worked in class. Sorry. Well, I have no regrets. This is actually, it's important for you. This, like physically speaking, this is a very important problem because it sets your bearings what you should expect when you solve a second order differential equation that appears in physical problems, which invariably have positive coefficients, right? So it's the spring mass system or the RLC circuit. One of those I would test on. Which one? Spring mass, right, yeah. Let's see here. Find the general solution. So here, if I ask you to find the general solution, I'm asking you to actually work out the constants. It would not be acceptable to stop and say the solution has the form c1 cosine x plus c2 sine x plus c3 cosine 2x plus c4 sine 2x. I mean, that's lovely, but that's like a third of the credit or something, you know. That's a very unfortunate mistake. Here, I asked you to find the general solution, so I actually mean for you to do that. And so when I do that, I calculate the derivative of the particular and second derivative, plug it back in, and lo and behold, we get yp is minus cosine 2x. Now I'm calling it yp1 because I think this is a substitution problem. See this? Notice this. Look out for this on the test. If I have like a three-part problem where parts A, B, and C, they share the same homogeneous piece, then you can use the principle of superposition possibly to build the third part from the first two. See, because this is twice, let's see here. So I got a cosine here, I got a cosine here. So what I can do is I can just take 1/3 of the particular solution to get that from part A, and I can take twice the particular solution from part B to produce this. Yeah.
I might be wrong. I might be very stupid if I am. The answer to the last one, you wrote 3 too high.
Oh, that's probably just a mistake, yeah. Oh, yeah, don't read too much into that. It's just me. So we got minus cosine 2x for the particular solution part A. Part B, we can't use undetermined coefficients because cosecant is not a solution that appears to a homogeneous differential equation. So we're forced to use the variation of parameters technique, which is general, but does require integration. So out pops minus x and log of the absolute value sine x. I have to remember, don't forget, the formulation is yp is y1 v1 plus y2 v2. Some of you on the quiz were just putting like v1 and v2 as the particular solution here. That's not right. You got to multiply by y1 and y2. And sometimes things simplify. So look out for that. Sometimes like you'll get a sine squared plus cosine squared, which could be important. The places that would be really important is like if I had a problem like this with initial conditions, simplifying your general solution will make your life way easier than it would otherwise be. But anyway, so that's my yp2, yp1. And you said I multiplied by 3 rather than dividing by 3 in the solution here. That sounds like something I might do. Oh yes, thank you. Good point. So this should be 1/3 yp1 because the force that's given in part C is 1/3 of the force given in part 1. So like the general principle at play here is just this, guys. If we have L of yp1 equals to F1, and we have L of yp2 equals to F2, same L, then L of C1 yp1 plus, let me not use C1, let me use like A and little b, because I don't want you to think of these coefficients as being anything to do with the homogeneous solution. This is just the method, this is the principle of superposition is what we're doing here. So since L is a linear operator, we get A times F1 here plus B times F2. I won't derive it, I'll just tell you how it works. So you just have to kind of, if you know this, and you see A F1 plus B F2, then you can do A times your first solution plus B times your second solution to build the composite solution like that. And again, physically speaking, this is very interesting because it corresponds to this method, the superposition principle, which says that if you have a linear system, the response of the system to a sum of forces is formed by a sum of the responses, just like that. Like you can view the net cause as a sum of the individual causes for a linear system. Yeah.
So the coefficient in front of the forcing force in the first equation, it does matter. Like the 3 in front of the cosine 2x does matter.
Oh yes. like the 3, so yeah, that 3 makes f1 equal to 3 cosine. And this makes f2 cosecant x. And that's my identification. You could label them however you like. Like you could have said this is 3f1, but that would have ended up changing. Anyway, there's various ways of labeling things, but yeah. Let me go on to another piece. There's another piece I haven't talked a lot about in class yet. So here's another couple of plain old variation parameters. Now I give you guys some advice, which is that if you're working variation parameters, it pays to simplify the Wronskian before you do too much calculation. So like here, if you do it carefully, you should see the t terms canceling out. And you should have whatever you have for your Wronskian, it should be positive. It shouldn't be able to be 0. All right, at least for the domain of definition for our differential equation. What's the domain of definition for our differential equation? For the nth order problem. What's the domain? What's the domain for which our differential equation is defined? Do you guys know? Back in test 1, I could have been any number of things, because I could have hit you upside the head with like a square root of t minus 3 or something, and then you'd have had to have the t minus 3 was greater than or equal to 0. Your domain of definition would have been 3 to infinity, right? That's where that expression would be well-defined real in the context of that one-dimensional, first order differential equation, right? Since test 1, though, we've just been working on what kind of problem? Well, second order, third order, sometimes first order, but always constant coefficient, right? The L for us has been universally, for every example we've worked, I think, L has been a constant coefficient thing. So the L, at least, the domain of definition for L is very boring. It's just everything. So any limitation on domain is just coming from our forcing function. So like here, secant, well, that's 1 over cosine, right? So that gets into trouble at, odd half integer multiples of pi. You got division by 0 there. It's hard to calculate in those spots. But so pretty much the forcing function will limit the domain for the class of problems we're looking at the moment. Now after test 2, we'll start looking at differential equations where the coefficients are functions, and then those will also play into the story. But for now, it's pretty much just the forcing function limits your domain. So what I'm trying to say is, the Wronskian doesn't involve the forcing function, right? The Wronskian is just based on y1 and y2, whose domain is all of the reals. So in our context, the Wronskian, it pretty much has to work out to an exponential or a constant, I think. Yeah. I would have to custom make a theoretical problem to make it otherwise, all right? Which I guess I could do. We have talked about the general theory of the nth order problem. So there are problems to be concocted there, but short of a student asking me a bunch of questions the day I'm making the test, it probably won't happen. Let's see here. Anyway, so any questions about this? So we have V1, V2, that gives us this, particular solution there. Let's see here. There, the Wronskian's 1. So you do need to know your basic trig integrals. Those are still with us. They're always with us. Let's see here. This problem's interesting. I wonder if did you appreciate what this problem is doing? Do you guys see what this problem does? What this problem is showing you is that you can solve integration by parts problems from Calculus 2 using undetermined coefficients. Basically, if I'm integrating a polynomial times exponentials, essentially, if you just look at it, you can see that the form of the solution has to be a polynomial times an exponential. So all you have to do is differentiate it, plug it in, equate coefficients, you're done. As opposed to doing integration by parts twice and trying to carefully, sort through all the signs. This can actually be faster than integration by parts at times. It's, borderline, but it's a nice trick to know about. Every differential equation, every integral equation, right? Anytime I do integration, I am solving a differential equation, right? Because what are you doing to find the antiderivative? If I say integral of x squared plus 2 to the x all times e to the x dx is equal to y, that means I want dy dx equal to the integrand, right? That's a differential equation, and we've learned how to solve those through algebraic means, right? So that's, I hope you saw what this problem was about. I know it's kind of weird, but you know, I guess it's friendlier to show it to you first on the homework as opposed to first on the test, right? Yeah, it has been a bonus question in yesteryear. Now this one here is something I probably should have talked more about in class, and it just never happened because, well, 8:15 I think. So, a couple things I should talk about here. The one thing I should talk about is a perennial issue. We have this problem, so let me talk about it. So I have y prime prime. Here's my favorite one. Y prime prime plus 3y prime plus 2y equal to, let's say, 0, right? How do you guys solve that? There are kind of two paths to go down here, right? You could do, okay, well that's, you know, lambda squared plus 3 lambda plus 2, which is lambda plus 1 times lambda plus 2, right? Therefore, lambda is minus 1, or lambda is minus 2, and we get y equals to c1 e to the, oh, see, I get to, at this point, I don't know. What do you guys want? What do you want y prime to be? T? All right, so t it is. c1 e to the t plus c2. So in this context, I can't take off points, right? Whether you go t or x or Batman, I mean, whatever. You can make the independent variable here, whatever your heart does happen to desire. So let me show you the trap that students fall into oftentimes. And I'm pretty chill here for the most part about mathematical abuse of notation. But there is one offense that I cannot overlook, and I will take points off of because it bothers me a lot. So let me show you. And I understand, I totally understand why you guys do it. All right, I get it. But don't do it. So this I can also write as d squared plus 3d plus 2, right? Acting on y equals to 0. That, so far so good, nothing wrong here. And the rules of polynomial algebra say that I can factor that. Like this, right? That, so far, still true. This is just the algebra of commuting operators. Any polynomial in D commutes with itself. Fine. Great. All right? Then the next thing I'll see students do is say D equals minus 1 or D equals minus 2. And then, you know, I'll give the student the benefit of the doubt to say that they're still going to write this. Right? Okay, great. There's just one problem. This line right here is completely nonsensical. It makes no sense whatsoever. D is the derivative. D in this context is d dt. I cannot say d dt is equal to minus 1. Like, this is not true. It's just not true, right? So this step right here, despite having good intentions, is really, really wrong and should not be written. On the other hand, this one here is fine because what's the difference? Well, lambda is a scalar, right? D is the differential, the derivative operator. So you have to be careful. There's certain things, if you go this path, which you can write, and there's certain things you cannot, right? To show you another example of this, if I have y prime prime plus, oh, I don't know, 8y prime plus 7y equals to 0, I do d squared plus 8d plus 7 acting on y equals to 0. I can do this. I can say d plus 4 quantity squared minus 9 7 minus 16. I wanted to make this, let me make this a 70 there, fixed. So what's 70? 70 minus 16 is what? 54. So plus 54, okay. And that's pretty much as far as I can go for the polynomial algebra here, unless I'm going to get complex, right? So what I'm telling you is if you go this route, and this is fine, and I would encourage you to, in fact, put this on your formula sheet, which is that when this happens, you can just write this. You can say, well, okay, so lambda is equal to minus 4 plus or minus I times the square root of 54. You know, you can write that. Or you can simply get to the point, which is to say y is equal to c1 e to the minus 4t cosine root 54 t plus c2 e to the minus 4t sine root 54 t, you know? And that would be fine. But what you unfortunately cannot do is say that d is equal to minus 4 plus or minus, you know, I times the square root of 54. Ooh, that's not a good sign. 54, there we go. This is total nonsense, all right? Okay, my rant is done. So that said, let's talk about this more interesting problem. So one of the things we can do is we can use polynomial long division to help factor. So if you don't know how to do that, then, well, maybe you should learn. So synthetic division is not your friend. It will not help you here because we're dividing by a quadratic. All right, so like if I tell you that y equals sine of 3x is a solution to this differential equation, that means that lambda equals plus or minus 3i is a root to the characteristic equation, which is tantamount to a d squared plus 9 being a factor of this differential operator, right? So I can factor out a d squared plus 9 from that. And I guess I just did it by rote algebra here. I just like looked at it and said, okay, well, have we d squared 9 here? Like parts of this are pretty much for free, right? If you look at this, you know that if it's a quartic, if you factor out d squared plus 9, there has to be a d squared here, right? And how do you get the constant up there? You get it from whatever this times that is, right? So that forces, since the 9 is given, that forces you to put 1 here, which pretty much means you just need to figure out this 2, right? Which, that 2 is a little bit complicated. It's coming, what has to go there, that 2 ends up determining, you know, this, and that as you multiply it out, right? So, I don't know, sometimes I can see it, sometimes I can't. If I can't see it, I will use, well, let me show you how I do that if I don't see it. So again, really shouldn't use the symbol d here. That would be an abuse. So I'll use whatever variable you want me to use for the polynomial here other than d. Like, we could use x, we could use t. What do you guys want? Lambda is probably not a good idea. We could use lambda. A? No, I refuse to use a for the polynomial variable. I know. Why did I ask? All right, so I'm going to use x to the 4th because this will make it most friendly. X to the 4th plus 2x cubed. 10x squared. 18x. All right, plus 9. And I'm trying to figure out how this factors. Yeah, I'm trying to figure out I usually call it the cofactor of x squared plus 9. And so we can just do long division, and that'll answer the question pretty quickly. So let's do it. All right, so x squared, and then that gives me x to the 4th plus, I'll put it over here because that's where it goes, 9x squared, subtract. And I get 2x cubed plus x squared plus 18x plus 9, which makes me put a 2x here. At this point, I'm pretty much done, but I'll keep going. 2x cubed plus 18x. It's good to check. So I subtract. I get x squared plus 9. Well, that's a good sign. Plus 1. So what this calculation tells me is simply this: x to the 4th plus 2x cubed plus 10x squared plus 18x plus 9 is equal to x squared plus 9 times whatever goes up there. Right? And then if I'm using this to try to understand the algebra of the characteristic equation, I don't want to stop there either, right? I'm going to go, okay, so that's x squared plus 9 times what? X plus 1 squared, right? So if I have this equation, this has solutions x equals to plus or minus 3i, and x is equal to minus 1 twice, right? I've usually used lambda for this. The book tends to use little r, right? You can use whatever letter you like for the polynomial algebra. There's just one letter I forbid. Big D. All right, that's the one thing, the one tree you must not eat from. Don't even look upon it. But do factor your operators. I know, you like. Anyway, any questions about that? So there's a, yep.
I know it's fair game, but can I put a question like this on recent tests?
Mm-hmm. Usually, yeah. I will try to test every nook and cranny of the algebra that I've shared with you guys. One of my missions in here is to make sure students leave differential equations with a complete and working knowledge of college algebra. I'm not joking. That's actually true. And I speak from personal experience. I really first truly learned certain aspects of college algebra when I took this course. It was differential equations that finally showed me, oh, I should know that algebra, and it shouldn't be a big deal. I should just do it. It's not that hard. Like completing the square is a good example. As we will see in the upcoming weeks, partial fractions decomposition, which you've seen kind of in Calc 2, but you'll see more of here. So anyway. Another thing to notice is, this should not be lost on you either, is this is a test 1 problem, right? This is a test 1 problem, but it is much easier to do it with test 2 technology, right? Yeah, I mean, you could use the integrating factor method, and you could go through all that, or you could just look at it and go, oh, so the particular solution is just a polynomial in x, plug it in, and write equate coefficients, plug them in, and done. I personally think this is much easier than the integrating factor method for such problems. All right. At least this is what I do if I'm in physics and I come across this differential equation, as is not unusual. If you're solving, for example, like an RC circuit or something, you come across this thing. It's really nice to be able to think of solving the problem in this way. Let's see, what else do I got for you? Of course, we got the spring mass problems. You know, you got to know how to set up Newton's law for the spring mass problem. There's not too much to remember here. Make sure it's on your card. If you don't have a, you know, an intrinsic love of the spring mass problem, then you should probably write down the Newton's equation. You probably should write down what M means, what K means, what B means, all that jazz. Let's see here. I think I've said pretty much everything. I don't know. I mean, let's see here. You know, if I ask for an integral solution, that means you can write the answer in terms of integrals. If you're trying to understand what I'm getting at here, relax. We haven't covered it yet. This is a comment from the future. All right, this is a future comment right there. You shouldn't. This should be just nonsense to you at the moment. All right. If you understand what that comment's about right now, you should probably come talk to me after class. You probably should just take the final now and just not even bother coming to class the rest of the time. All right, like that's the kind of understanding of differential equations I would see a person who understood that comment right there. Anyway, I'm not sure I'll even cover that this semester, honestly, because I keep missing stuff at the 8:15 spot. What have I missed in this particular part of the story? By the way, guys, if you go back to the notes, you should notice there is a whole section that got left on the cutting room floor, right? Like, check this out here. Well, Cauchy other problems we'll come back to. But like this reduction of order section is a very interesting calculation. And essentially it shows you that you can use, and I don't know if you even know about this or not, but this is like the nth order product rule. Did you know there's such a thing? Well, there is. There it is. And using the nth order product rule, you can take the nth derivative and rewrite it as such, and then you can plug that in to the given nth order problem, and it makes it into a n-1th order problem, if I remember right, which is kind of snazzy. And then you can just keep doing that. So it's most interesting in the order 2 case. If you make this reduction of order for the order 2 case, then you take a second order problem, you do reduction of order, you get to a first order problem, this one, which then you can solve with the integrating factor method, and out pops this solution, which then you integrate, undo the substitution, integrate, and then you get this like bizarro formula for the second linearly independent solution from the first. The second linearly independent solution for the n equals 2 problem is y1 times the integral of 1 over the first independent solution times the exponential of minus b over a times x dx. I mean, the first time I saw this is in Nagel-Saffensnyder. It's in your textbook. And I've taught this in the regular story arc of the course before. But it's really just kind of a theoretical curiosity. One of the reasons this is interesting is in the case of the double root solution, this ends up producing the xe to the, it produces the te to the t type solution again. It's another way to derive the repeated root solution. But this is not on the test. I didn't even talk about it in class until today. Obviously, that wouldn't be fair game. And then the other thing that this is more fair game, and let me tell you why. Why 3.7 is a little bit more in the realm of possibility for the test. Not directly all these calculations, mind you, but the idea of this section we used to derive the solution to d minus lambda to the kth power. How did we do that? How did we derive the solution set? We made a substitution, right? And so that's what's done in this section. Basically, if we assume that the differential operator is a product of operators, then you can make a substitution, like z1 is the product of everything except for the first one, and then you just end up with L1 z1 equal to f. Well, that is this, which you can integrate by the integrating factor technique, and you can get the solution like such, and then you can let z2 be these guys, and you've got L1 times your you get z1 is equal to L2 z2, which again is a first order differential equation which you can solve. So all I'm trying to tell you is if the differential equation can be written as a product of operators, you can solve it by repeated integration using the integrating factor technique. It is quite a calculation, and but there's the sketch of it in general. So like here's an example. If I have L1 is x dx and L2 is 1 plus d dx, I can solve L1 and L2 equal to 3. To do that, I make a substitution of z is equal to like y plus y dy dx, which makes me have this. I solve that. It gives me z equals to this. And then I plug that back into my substitution and solve that. And after a short calculation, I will find y equals this lovely beast, which means that my general solution has this form. Now, did we see anything like this? No, we've seen nothing like this. This is way outside our ball game at the moment. And the reason for that is this differential equation is one which has a variable coefficient. See that, x d dx? That's something we haven't dealt with yet. So now the 1 plus d dx, that we've done. That's constant coefficient piece. What's interesting here is if you solve the other way, So if instead of solving L1, L2, y equals to 3, you solve, say, L2, L1, y equals to 3, it's a different differential equation. They're not the same. Because here, L1 and L2 do not commute. These are not commuting operators. So like some of the stuff we've done, and here it is, like the next example, I solve the other way, and we find a different solution. All right? That's because these operators do not commute. It's important for us to be aware of that, because after test 2, we'll look at the Cauchy-Euler problem, which is another place where you have differential operators which don't commute, so you have to be careful. We have not had to be careful about that, see, because d1 plus d2 is d2 times d, like these polynomials just satisfy the usual algebra. Like I can factor this just like I usually factor things. Things move around just like usual. There's no kind of funny business with these, with a polynomial in D. Anyway, and then besides this, you know, make sure you look at the quizzes. The quizzes had good problems, yeah? So anyway, I'll see you guys Wednesday. I'll try to bring the test here 5 minutes early and let you end 5 minutes late, so you have an hour. Not that it should take an hour. How many problems would you like?
4.
4 problems? All right.
Six.
Oh, 6? Oh, you changed your mind? Okay.